Good morning, ladies and gentlemen, conservators, artists, color enthusiasts. So, by chance, my visit over here mixes with this class this morning, and I'm asked to give you some ideas about how to think about pigments. This here is a little handout from about 150 years ago, and it's written in here: a pigment is a material from which a dye, paint, or lake may be prepared. A pigment, therefore, in our case, is the refined and purified coloring matter ready for mixing with some vehicle. That's a little bit short, and I doesn't think it's enough to use it like this for the vast amount of pigments available these days. When I started my business nearly 50 years ago, I'm an old guy now, then there was no handling of my need to classify pigments somehow. There was a book called the Color Index, but the Color Index just knows colors like yellow, red, and blue, and puts every pigment one after another, whatever pigment it is. That is not helpful for the use of pigments. When you look at the color charts of artist pigments companies, the colors are just sorted like there is yellow, green, blue, or whatever color, but it doesn't specify what specific differences between the pigments might be. And therefore, my idea was, in these early days, to classify a little bit according to groups. We did have one group that was the group of pigments what we produced in my business in the beginning until today. We started with the number 1 or 10, or in the meantime it's the number 10,000, but it was starting with the first pigment we made. That was smalt. This smalt thing is a very strange pigment. It is colored glass, but it's definitely an important pigment because even the people between Euphrates and Tigris used it about 5,000–6,000 years ago. So the first pigment I had got this one, number 10,000 nowadays. And then everything else we started to produce got a number according. The blue one, the yellow one, the green one, all just how it came up to be produced. But that is not a numbering system that works for a bigger amount of pigments. The next thing we thought about was finding a way to cluster around properties of pigments. And the first cluster was the cadmium pigments, yellow, orange, red. And these cadmium pigments got a group together. Till today, I think it's reasonable to have very chemical similar things grouped together in one group of things. They behave very similar. They have very similar properties. And that is a group of cadmium pigments. And we did the same thing with the iron oxide pigments. That is a group of pigments that are man-made, synthetic, but they behave very similar. So this was two groups. But the biggest group what we had at this time was the natural earth pigments. The natural earth that goes from nearly white to nearly black to green to red to yellow, all comprised in this group of natural pigments. And to a certain point it might be okay, but I think nowadays you should have been a little bit more careful to find a little bit more differentiation with this group of pigments, to have the manganese differently to the iron oxides and things like that. The next subject we came up was the traditional mineral pigments. What is man-made, metal oxides, metal sulfides, metal whatever compounds like cobalt blue, like ultramarine, like zinc white, things like that. We just stick to the colors. To make an extra chapter for every single one would make endless chapters. We need to have a chapterized system somehow. And it worked out nicely. Most people do understand this by working with these things. Green pigments belong to the green pigments, red ones to the red ones, and so on. That worked out nicely with the organic synthetic ones like alizarin matter, of phthalo blue, things like that. We have there a group of things man-invented, man-made, what behave differently to all the other groups of pigments. So we can go on and on with this and find special group for the metallic powders and a special group for the mica powders and a special group for whatever there is a special group of material we can put into with a special name on it. And that worked out the last 40-something years. But I'm still thinking about that it is not really the ideal checking for the pigments. We should find something what is more related to the way the light interacts with these different groups of things. You know, a pigment is something what doesn't dissolve in the binder. A dye is something what dissolves in your whatever medium. That's the difference. The one is like sugar, the other is like sand. And this is a hint to the big difference between the most pigments and the most dyes. When you look at these sugar molecules, if that is a colorful molecule, it's a dye, like whatever dye you can think about. And this dye is going to dissolve in the water or the solvent and become single molecules. And these single molecules behave like independent centers for color. Therefore, the dye is highly transparent because it's only single molecules. It is highly tinting with an extreme tinting strength. And because it's a single molecule, it's highly receptive to the energy of light. And nearly all of the dyes we have in the world are not light fast. Because the dissipation of the energy within the single molecule is not fast enough. There's not enough way to dissipate the energy. And after a while, looking at the single molecule with the high energy of the sun or of the light, and the molecule is going to break down. It is like not made for high energy consumption. Another thing is a body of color like this. When you put this out into the sun, what do you expect? It's going to last forever. Whatever temperature you can achieve with the sun, 80 degrees Celsius, 100 degrees Celsius in the full sun of the high noon, it's not going to be damaged. There is enough solidness to dissipate all the heat out of the molecules, out of the crystals of this thing, and we do think about things like this as crystals who can dissipate the energy in the crystal structure of the entity. It's not about a single molecule. It is about a group of atoms, many different atoms, who form the crystals and who all together have a structure. Like you can think about many bricks forming a wall, or many solid things forming an entity like this stone. And therefore, these solid crystals have a reputation for high light fastness. Nearly all of the natural stones you can think about, not all of them, but nearly all of them have the ability to withstand heat, temperature, and light to a certain amount, a few hundred degrees, long time standing in the sun, lots of water without being dissolved or bleached or damaged at all. Therefore, this difference between the crystalline stuff, what makes up nearly all of the mineral pigments, and the natural crystalline stuff like malachite, mercury, sulfide, cinnabar, amber, or whatever you could think about, all these things are made out of a huge amount of units who form together a unit what we call a crystalline structure. You don't necessarily see this crystalline structure. There are things like this pyrite. You see easily this forms a cubic formed crystal. But even if it looks like this here, what is a hematite, you don't see the crystals. Everything in here is, when you look with a high resolution microscope, it's highly crystalline. It's not amorph. It's not single particles. It is all units of this Fe2O3 hematite building a structure. And the structure is able to withstand whatever you can do to this. Light, the next 10,000 years, who cares? That's going to stand. You see, therefore, perhaps we should think about something more like how the light is reacting with this. Within the dye molecule, the light reacts with the electronic structure within this one molecule. And if there is some resonance, or however you might call this in English, I don't know, and this moving of the electrons is responsible for the color you can see. Within the crystals, it's more like you have the metal atoms or single atoms, and the light coming in elevates the energy level of some electrons, and what is not absorbed is being reflected, and you see that color. And that's not one single atom or a few, that is a huge number of atoms, each being part of the system, and the dissipation goes all around. Therefore, good dissipation, good standing. We could think about other things like this. This is a mica. I can hand this around. So, and the mica is something what is a crystal in a form like a sheet of paper. It is small sheets of paper. You see here that is not a big, it is small particles who shine. And these particles have a surface what is like being a sheet of glass. It's clear, it's even, it's sober. And this gives the light the ability to have a reflection like with a mirror. And this mirror-like reflection is more or less without color. If you have a colored light, this mica will reflect the color, not like other things. If you put a light, colored light onto here, you don't see the light so much. You see something strange because the reflection and the absorbance will be different. So this reflection of the light and the reaction of the energy of the light with the thing what we call color, this is going to be of high impact on your work. When we look at these dye-like molecules, or the modern synthetic organic things like metallake of tyrosine, blue, things like that, you can grind these things to an endless way. The finer you get, the more productive this pigment will be. Because the color is located within the molecule. With the crystals, it's different. When we look at, let me say, colored glass, it is blue colored glass. I can hand this out and you can feel it. So this blue colored glass looks perfectly dark blue. But when you grind it, the more you grind it, the more the centers, the cobalt ions in the glass are separate from one another. And in the end, if it's fine enough, it's a slight grayish powder when it's ultra fine. We don't do this, we stop early to keep it a color. But if you keep on going with the glass powder, you end up nearly with white powder. Because the crystal is destroyed in this matrix. And without the crystal, the color doesn't work. It is not just the single ion, it is the group of ions what makes it the color. And that is with the ultramarine, with the hematite, with the smalt, it's always that you need a big number of ions together in a crystal to make it a color. That is, if we take something simple like malachite, this is malachite, a green copper carbonate. And this green carbonate gives us a wonderful green powder. We call it malachite powder, green malachite. And when we grind this and we're going on, and we come to the nanoparticles, let me say 2 digits nanoparticles, this thing is very pale because the crystals are damaged. And the amount we can grind these things depends on the different material, of course. All the crystals are different. But it's important to understand in the medieval times, in the times 2,000, 4,000 years ago, people didn't have much modern-like pigments. They did have these natural things from earth, from the mines. And these people were limited to a certain milling state of the pigments. Nowadays, with the modern particles, we can do car washes on the cars with particles below 100 nanometers. That's extremely fine. And the layers become thin and thinner again. But that is not true for historic painting. And modern painting, to a certain point, is depending on a mix of these historic pigments and the modern ones. So we need to understand when making pigments and making a paint that some of these pigments need a certain thickness of the layer to be fully opaque. It's not a lack of quality of this pigment, it's a lack of this unique molecule-like thing, it is because it's a transparent crystal in the end, what you have in hand. And that is what I wanted to explain this morning, that the ideas we understand pigments is to understand the physical reaction, what the light is doing with the surface of this thing to give us a color. There are many different ways nowadays. When you look at the pearlescent things, the interference things, there's lots of modern ways to look at color. One of the modern things is when you look at an iPhone, at the camera of the iPhone, there's a little bit black around the lens. Have you ever seen the black around the lens? And in the early days, this black got painted with a high tinting black pigment. We did supply to Zeiss Econ black pigment and brushes to paint the surroundings of big lenses in the past. But nowadays, the high quality is done with a little laser, and it makes little steps, and the steps are like slits, and the light is being bent by the edge of this step, and the bending is just such engineered that there's no reflection left. All the bent light is being bent again and again, and there's no light coming into the lens. You can imagine? Well, it's complicated, but it's a modern way to use just physics to have a perfect black surface. And between this and
texture, it's not.
It's only texture. With the modern ones, not with the old ones, but with the modern ones, it's only texture. Perhaps you've heard about the black of Anish Kapoor.
Yeah.
That is texture in a traditional form. It is tubes, and the tubes have a certain roughness inside. And the light going inside the tube doesn't have a chance to come out again. If the light goes in, then it's black. That's the definition of black. You look into something, nothing comes back, that's black. The trick is you need to have it made in the high vacuum, and you need to get them all aligned. You need to do this with a strong magnetic force to have them like that. It's not feasible in a studio, but it's very black. So from this starting out, being crystals and molecules, going to the modern structure-induced colors. That's what we try to span with the Kremer Pigments assortment. Any questions?
I have a question. I was at the Museum of Natural History recently, and they were saying, what is a rock versus a crystal versus a mineral? And it said minerals are made up of crystals. So what differentiates the definition of a mineral versus a crystal?
That's the size.
Yeah.
So see, we call things to have a crystalline structure. Mm-hmm. And this crystalline structure happens in very, very small measurements. These things usually happen to be not like this. That is nearly an inch, what this crystal of pyrite is. That's very rare to have crystals of this size. Imagine most of the things you see don't have crystals you can recognize. Let's think about marble. Marble is a calcium carbonate, and whatever you see as a limestone, as a marble, is the same chemical composition. It's calcium carbonate. Chalk is calcium carbonate. And when you look at chalk, this thing what you have on the walls, and you look at this with a microscope, you see little crystals. When you look at a limestone, you see with a loupe the crystals. When you have a Greek high quality marble, you see a quarter of an inch crystals in the marble. And if this stands out as a single thing, we call it a crystal, a collectible crystal. There are mineral stores all over in the city where you have crystals like amethyst, like crystal mountain, like whatever crystals. That is the collectible stuff. You pay for the beauty and the big size of these things. But when you look at this here, you don't see the crystals, but it's nothing but crystals. But very, very small ones, enough to dissipate the energy. And the difference, simple spoken, when you see something in a crystalline form, then it's rare, special, and you call it collectible. And if it's just the same, but not in that form, you might call it a mineral.
This is just as resistant, like
Actually, the color of the amethyst is not light resistant. There is a trick with this. It is depending a bit on the light and the humidity in the crystal. And if you put an amethyst out into the light, it's going to become brown. It's a pity, but not all of them are good. Most, but not all. The amethyst is going to become brown in the sunlight. In a collection without sunlight, it stays. The sun is a very powerful thing. It turns the dissipated iron in the amethyst into oxide, what is brown. Any more questions? Good. Yeah.
So you're gonna have two stones that you ground down into powder. They become pigments.
Yes.
If I join them in some kind of a liquid, will they actually fuse, or will they always swim next to each other?
I do not really understand your question. You have two stones, you grind them into powder.
Will they become like a pigment?
Yeah. And then you can mix these two pigments into one. You can do.
They will fuse with each other.
The particles say, whatever two pigments you mix, these pigments are not supposed to react one with another. They are the thought of being two entities staying as two entities in the mix.
They become a new entity.
They became a new thing, a mixed pigment. But they don't become a new one thing. They resist like they would do a single ones. But that's like you mix two pigments, you get a color in between perhaps or whatever. And this is going to be a new color. But it's two pigments making a mixed color. You cannot get them out again. The dye and the pigment can be mixed. There was a guy called Rothko who did this. And he did a lot of his fancy colors with the dyes. And because of the light fastness of his paintings, the collectors got difficulties. the paintings that don't have mind, I think. They got damaged by the light. They changed quite a lot. So that's because of the dyes he used. Pheasant and Pearl was a famous company over here. It was applied Rothko with the dyes, and these dyes were not meant for art. Cheap prints in newspapers, cheap children crayons, they often contain dyes. Therefore, if you look at an old Life magazine and you put it in the sun, it's going to change in the next 2 weeks. Because the dye is productive, cheap, fast, brilliant, but not made to last.
Is there a way to achieve that brilliance without using dyes then, with using pigments that are...
There are pigments who are nearly like dyes, yes, but you don't have the variety with the pigments. You can mix a bit and come up, but the transparency and the brilliance is the domain of the dyes. You always have to get a little bit of opaqueness into this to get the stability. Not much, but at least a bit. Yes.